Hello guys, welcome again in another video. In this video we will discuss about negative voltage, buck converter for negative voltage. So the thing is, here you have a negative voltage at the input, and you want a negative voltage to the output. So for instance, you have minus 30 volts, and you want a circuit that step down this voltage to minus 12 volts. 30 volts, 12 volts, for instance, 10 amps, 50 volts, for instance, 50 volts, 10 amps, and here you have minus 30 volts, 5 amps, something like that, with an efficiency of 95%. There are not so many circuits like this around, and this is called, for instance, we can call it negative buck. We can use this controller here, which is called LTSPICE. This is a controller with the proper configuration can allow you to have a negative voltage at the output, provided that you give a negative voltage at the input. So let's see how the circuit does work. First, as you can see, it is a little bit different from the classical buck converter, because here you have the two switches. Okay, you have the two switches of the buck converter, but because they are negative and they are grounded, these two switches are in the are sourced in the ground direction. So the source here is in the ground direction. The source here is referred to minus Vin. So you have to make this accommodation here. It is not immediate, the translation. So you do know that the buck converter is this Vin, the two switches here, and the inductor plus the capacitor. Okay, to make a minus Vin, you should ground this instead and transport this guy here. And if you do that, you will see that this switch is referred to minus Vin, and this one is referred to the ground, like is shown here in the figure. If you do that, you will create a network pair, a switching pole network, which allow the discharge and charge of this inductor here, namely turning into a buck. Because as you can see later, here you have the inductor and the output capacitor. So at this point here, you're gonna have the classical square waveform, negative, and the filter, the LC filter, will transform it into a DC component, into a DC voltage. Now, in this controller, there may be some pins that you're not familiar about. So let's discuss it a little bit. Let's start from the ground. The ground is grounded. Then we have the enable feedback pin. This is this is referred to minus Vin as always, and it is used to have enough voltage to start the internal logic. Inside this guy there will be some latches for the current control, and also some LDOs for the power supply. The LDO is used by the int VCC and must be referred to Vin. Then we have the mode. The mode is basically, as reported here, is basically the DCM CCM forced continuous mode. If you want to work in DCM or CCM, you have to follow what it says here. By the way, we will connect it as the application note suggested. PG is power good. It is an indicator which basically advertises you that everything is working correctly. Then we have the RT pin. This pin basically set the frequency, the switching frequency of your converter. As you can see, everything is referred to this part here of the circuit, to this net here of the circuit, which is still minus Vin. So in a normal controller, you would have all this pin here referred to the ground. If you do remember that you have the soft start, this is the frequency, and it was referred to ground. The soft start, it was a capacitor and to ground, because the soft start had basically a mirror current inside, and you could select the capacitor to charge the ramp like this with a constant current of the mirror inside. Then you had the current compensator CA, which is always a type 2, like this. Everything referred to ground. The feedback pin, the int VCC, everything was referred also to ground. In this case, it's not. It's referred to minus Vin. So you have to just to invert everything in your mind, and then it will be clear. As you can see here, the bulk capacitor is polarized plus with the ground put in here, and the minus is the minus here. Why this? Because because the minus here and the plus here symbolize not the plus and the minus like we always intended, but superior and negative, superior and less voltage. So it's not that if you put negative voltage on the polarized capacitor, it will explode. Not like that. But what you have to do here, is to give the voltage on the A side. The voltage on the A side must be greater than the voltage on the B side. So in this configuration, it is correct to put the plus on the ground, because you will have negative voltage on the minus. So you have minus 30 volts here, and you have 0 voltage here, and it is correct like this. Plus and minus like this. So it is still correct. Pay attention in this in the second part of the circuit here. As you can see, something changes in this part, because as you can see here, the feedback is grounded. The feedback is grounded, but not only this. Also, the capacitor is inverted again, because this is the output voltage node, and you have the reference. You have the positive reference of the feedback here, and it is still grounded. But of course, the equation will be different. For this reason, I reported the equation here. As you can see, it's quite different from the classical divider. Other pins to note is the sync. If you use multiple controller of this, they will be synchronized thanks to this. Minus Vin, which is here. Emon is the current monitor. It as you can see, output current sense monitor. Its voltage is referred to minus Vin pin, blah 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 blah. It's this equation here. And you can check and limit the current thanks to this pin. Soft start capacitor is the soft start ramp, as you always know. VC is the type 2 compensator. This is the type 2 compensator, and as we know, it is the classical transfer function like this. This compensates the 1 over 2 LC, because this is the transfer function of the back. And so if you sum these two, you will have, as a result, this. Okay, simple as that. And the feedback pin is the feedback, as you can know. And then we have all this group here: ISPN, ISN, CSN, CSP. Now, basically, this is the current sensing, okay? CSP and CSS the current sensing, and this one ESN ESP is to use to limit the output to load current. Thanks also to Imon. Then what else? We have BG, we have BG and TG. These are the true square waveform used to turn on the MOSFET. And that's it. I think that we can open LTSPICE. I explained much, okay? We can open LTSPICE and build our own model. So we can use this. Okay, so first thing is to put the ground. Let's put the ground immediately, and let's put 20 volts. I will ground this in this way, so that everything is referred to minus V in, like this. Because I put the ground, I put the ground to the plus, and so you have minus 20 on the other side. So this is correct. So now we have to ensure the efficiency of the buck capacitor. So let's use like the application note suggests, is 120 microfarad in this way. Still referred to minus V in. And I must have the space like this. Here we said how much? 6847. Okay. The switching frequency we will set to 250 kilohertz. So it is set to 103. Int VCC and mode are shorted altogether and referred to minus V in with a capacitor of 2.2 micro. Let's make the circuit a little bit compact. Then we have the ground. And we have also the enable feedback pin, which is basically a divider. NK and 62. Let me make something like this. Okay, so now it is correct. Then we basically did almost everything. Let's put a capacitor here, refer to ground. 1 micro is enough. 2 micro is enough. So now we need to design the buck converter itself. We use the MOS. Again, here it is sourced to the ground, like this. And let's pick okay, this can be good. Lower on. Okay, this I like this one. And let's connect this guy here because this is the high side to the TG. And let's use another one. Oh, I need some more space. I need more space. Okay, so since it is a low side in a back, let's choose the one with the less add-on, but of course with low gate. This can be good. Some less add-on resistor. Okay, this can be good. Because this switches, okay, this switches, and so it has more switch losses, and this guy here has more conduction losses. This guy here can even achieve 0 voltage with the right time. Let's put the shunt of 2 milli. This is referred to CSN, and this is referred to minus V in. Okay, I will teach you some beautiful thing. You can use a special wire arc. I remember that it was somewhere in references, maybe no, in I don't remember. It was called X. I don't remember. It was like an arc. Autogeneric comparators contrib no. No. Miscellaneous maybe. Ah, yes. It was Jumper. Aha, found you. You see? Beautiful. Then you hide this guy and you're done. Oh no. How did you... Ah, okay, it was like this. Yes. I did remember how to do that. See? You pick this guy and plug it here. Ah, finally. Thanks. Now, this guy is connected to BG, and this guy is connected to TG. Like this. For this reason, jumpers are useful. Because I can do this, and can do this. No. No. What is this? No. Come on. Okay. Thanks. Okay, so now we have the two switches. Let's use the inductor suggested by the datasheet, which was 7.3. 7.3 microhenry. The shunt of 4 milli. We will connect it to here because this is the current load limitation. Let's set it to 24 volts. And we can put the bias to ground like the application was suggested. The power good we can use just this pin vacant, and we can put the output capacitor basically to 300 micro like this, and we can use a resistor load of 1.5 ohm. We can call this out. Okay, this node will be a switching node. So switching node, output node, okay. The feedback, of course. So the first resistor is 32K. The second resistor is 49.99K, according to this. Okay, everything seems good. We miss the VCC, 100 pico, and the other branch, 5.9K and 2.2 nano. By the way, this is horrible. Really, really, really horrible. Better like this, honestly. Let's call this file as negative negative buck converter, and let's run the simulation for 2 milliseconds. I hope that everything is correct. Let me check. Let me check if I missed something. Ah, yes, maybe we can put a series resistor of 1 milli. This will speed up the simulation also. And we can even skip the initial operation point, I guess. This way will be way faster. So the first thing that we want to check is the wow. So this guy is not switching. I just probably made some mistake somewhere. Yes, because the it's very easy. Minus 24 volts. Okay, so the negative one, there is a negative one. Maybe because I skipped the initial operation point solution. I don't think that's the problem. Ah, okay, I missed the okay, I missed the CSP. I missed the CSP. Let me lower everything here. And as you can see, even a little mistake can cost you, yeah, can cost you everything. Even a little mistake can cost you everything. So BG is set to minus, BG is set to this guy here. Ah, yes. That's because this guy is not working. This must be a PMOS. Sorry, I didn't notice, but this must be a PMOS, of course. Otherwise, it won't switch. It won't turn on because you're giving negative voltage here. Sorry, I completely forgot that this had to be a PMOS. But the switching node is still not working. So there is something not working, maybe in the... I'm checking. Yes, I missed a capacitor here, but that's not so important in my opinion. It can be the reason. Probably ground enable feedback pin. I think that that's correct. Ah, yes, the soft start is too high. Okay, the soft start was too high because no, this is too this is too high. For 705 is obviously too high. I think that this is too high, in my opinion. So this is a mistake in their application note. That's a bad mistake. That's maybe the reason it was working. The power code is -24. It is correct. Yes, so everything is working in here because you have the right voltages. Okay, so you have the right voltages, so everything is working here. Ah, okay, now it's working. No, guys, this was impossible for me. So if you follow this and you put this capacitor here, it was impossible to make the simulation work. Now it is switching, so it is, of course, it is working, but it was impossible for anybody to uh, make the simulation work. It was really impossible. So now if you check the output voltage, as you can see, the ramp of the source start is charging, so we need to put at least 10 milli. No, sorry for the delay, but guys, really, it was impossible. So how could I know that the soft start pin was too high? It's possible. This is wrong. Based on my experience, the soft start pin is like 10 nano, 20 nano, something like that. And this is too high. Too much high. So let's run the simulation again. And now it's working. Gosh. It is not even overshooting. So this guy here is tuned very well. So let's check the switching node. And we can stop, I guess we can stop here. So this is the switch node. Very strange in my opinion. Very strange. It shouldn't behave like that. But the output voltage is indeed correct. Let's check also other pins. VC. This is the compensator. Let's check, for instance, the inductor current. Okay, it seems good to me. Let's check this is the contrary. Seems good to me. Okay, so they are forming inductor current. It's correct. And I think that everything is working fine. Finally, I would add. And guys, I think that the last thing that we can check at this point is to put a dynamic load, because this is a closed loop, and as you can see, you have 8 amps and -12. So the power is 98 watts, and the input power is you have to make the average of this. So you have 136 watts, So let's make a very, very fast calculation. 130, sorry, this is 98, so we have 100. Let's make 100. 100 over, there are some spikes here. No, no spikes. We can take this and make the integral 136 over 136. We have 73%. Okay, so this is not the best efficiency. Maybe because we choose the wrong... maybe because this is dissipating a lot. Yeah, 37 watts is unfeasible. What is this shit? Ah, sorry, I put this guy here with a resistor of this. Ah, okay. Sorry, I put one randomly. Let's choose, I don't know, less Aron resistor, like 2 or 3, like, and the low gate resistance. Yes, this can be fine. But even this can be fine. So let's do again, everything, and let's check the dissipation of this guy. This guy is dissipating nothing. Okay, so this was well chosen. Now let's repeat everything. Sorry guys for before, but now we have to check the power dissipation of the MOSFETs. Ah, now the output power has increased. The output power is the same, but the output the input power should decrease. Okay, let's check now. Okay, let's check this guy now, and we have half. It is still a bit high, too high, definitely too high. And I don't know why it is too high, honestly. We have to check the... Ah. Okay, we have some big spikes. We have some big under spikes. And that's probably because... okay, everything here is referred to the minus V in. And this is referred to minus V in as well. We have to put the minus in one of the two. Okay, so the dead time is big enough to avoid short circuits. I think that, yes, it's big enough. Yes, 100 nanoseconds is big enough to avoid short circuits. Maybe because there are some spikes and that's it. And the power dissipation is way higher than it seems, because the MOSFET is not that bad. Is not that bad, the MOSFET. You can reduce... no, that's the best compromise for the PMOS, I guess. 3.2. We can do one thing. We can take the lowest gate charge of the market, like this, and we can try to make a parallel of the two, so that the resistance will be reduced. Yes, but like this, I can't. I honestly can't. Duplicate overlapping components. What? Let me check the dissipation of this guy. Of course, integration is possible when the program is running. 1 watt here, and the other guy... Ah, as you can see, I definitely 2 watts of 1 watts and 1 watts of dissipation is now a feasible circuit. Thanks. 1 watts. So we reduced 1 watts and 1 watts. I don't know, maybe the current now is more acceptable. Yes, definitely more acceptable than before. So let's check the input power. The input power, let's check the input power. The input power again is 100. Oh, okay, now the dissipation is correct. So we have 98. We have here we have 101. We have 101. 101 and what? 101.61. And here we have 98 over, oh sorry, it's the contrary, 98 over 39 over 91. This is what? Dot 61. We have an efficiency of 96%. Now it's very good. Now it is very good, it's well designed, and also the proper dissipation of the MOSFET. Now this circuit is really feasible. Since this is a low side, this dissipates nothing, as I said before. 642 milliwatt is basically nothing. And we have at the output, we do have 100 watts. So it is everything is correct. This is 0.5 watts. All feasible dissipation. Okay. The dissipation of the inductor is nothing unless you put the DCR inside. Let's check the dissipation of the shunt. Okay, so this dissipates how much? 260 watts, 260 milliwatts, 260 milliwatts. Okay, and this should be half. No, because the current is different. So 700 milliwatts. 700 milliwatts. Thanks. At full power. So we have we have basically almost 4 watts of losses. Almost 4 watts of losses. We can check the datasheet and we should have something like that. So it doesn't matter. So now the only thing, so we designed the circuit. We put the thermal MOSFET. We put also the thermal MOSFET, and now what we have to do is to check the drop voltage during a pulse load. So what we have to do is now to put R equal if time is greater than 3 milliseconds, 3 milli. This resistor is equal to, I don't know, 1.5. Otherwise, this resistor is equal to 3. So in this case, we will set the resistor the default to 3, and then the load will step to 1.5 after 3 milliseconds. So now we are not interested in the dissipation. We are just interested in the output power and in the load. So first, let's check the load here. And in the other part, let's check the output voltage. That's everything that we will need. Let's run the simulation. Please let me put a negative here because otherwise I can't understand nothing. Let me put negative here. Now at 3 milliseconds, there should be a peak request in the output current, and he should overshoot, and then restabilized in a if we put the minus here, that's the peak. Okay, I am requiring a step current right now, and he reacted very fast. So let's say in a zoom, let's stop the simulation. So that's the part of interest. As you can see, I have a very few drop voltage, just 160 millivolts. Okay, just 160 millivolts of drop voltage here, and just I can say just 40 millivolts of peak, 40 millivolts of overshoot. Wow. So we have 106 millivolts. So as a peak drop, we have as undershoot we have 140 millivolts as undershoot. Wow, that's really something, guys. It's beautiful. Just 140 millivolts undershoot and 40 millivolts overshoot. It's really, really, really stable and beautiful. I think that we covered everything, even the dynamic part. The last thing that we want to check is if this circuit is stable, but it is. To see if it is stable, just open the FFT. So view, FFT of the current zoom extent of the data, of the output voltage Vout, and what you should have is just the component of it's just the component. And as you can see, you don't have any components in the under the 100 kilohertz range. You have just the switching components and the harmonics, the double harmonics, 2F, 2F, 3F, and etc. So the circuit, as you can see, is well designed, both thermically and dynamically. I think that we can end the video here with a 96.8% of efficiency. Negative buck converter. I think that we can end the video here. Sorry guys for the delay before, but it was necessary. Thank you guys and see you in the next video.